Okay. Hi, everyone. Please appreciate I spent the past half hour growing the font size on my slides, just so you can read code from them. So I'm Yannis Smaragdakis, and I'm an academic researcher by training or by background. But for the past few years, we've founded together with Neville Grech, who's somewhere in the room, but over there, we founded a company called Dedaub. Sorry. So if I ask the broader Solidity developer population, I'm sure most of you have not heard of Dedaub, but we are, take my word, we are fairly well known in the security community, in the white hat hacking community. And part of the reason, a large part, is that for many years now, since 2018, we've been running this site, that's ours actually, contractlibrary.com, which is kind of a contract code explorer, which, well, why would you need that? Well, if you're just developing, you probably don't need that. But if you're trying to do some security analysis, you probably do need that. And this is definitely too small font. But the point is, you can go there and see any deployed contract on Ethereum. Let me try to grow the font a bit. So these are the hottest of the past 20 or 30 blocks or something. And so if you go in and click on some contract, and my network comes off my phone right now, but the idea is that you can see, even if it doesn't have source code, you can see a decompiled view of the contract. You can check, say, its storage variables. You can check, well, not exactly the most responsive right now, probably because of network. So you can check storage variables, you can check approvals, etc. But the main thing is the decompiler. Anyway, this is a service that we've been running, like I said, since 2018, so close to 4 years now. And it's fairly useful, especially when you have like an attack contract and you're trying to quickly decompile it and see what damage it may do. So, but really, what's our technology as a company? We are really having a vision of trying to build programs that understand programs. So we come from a program analysis background. We build program analysis technology. Everything we do, including the decompiler, is written in logical rules. So we have rules that look like this. And of course, you cannot really closely understand this. But we build concepts by having thousands of logical rules. And these concepts do anything from decompilation to deeper program understanding. And based on this, we have built this system to try to detect vulnerabilities, to try to detect defects in deployed contracts. And that's our watchdog system. And in the past year, this has been pretty successful. So it's been behind many, many vulnerability disclosures that have been fairly visible. And maybe you saw some of these, one or couple of these articles, but they have been pretty visible vulnerability disclosures, 9 high-profile vulnerability disclosures that got us some bounties that are about 3 million right now. So pretty significant vulnerabilities found through this analysis technology. Now, why am I here? What do I have to say? Well, basically, it's just a disconnected collection of items from my experience. And what's really my experience? Well, a couple of solidity patterns that we've seen in vulnerabilities, not selected by any sense of seriousness, but things that we have found to actually lead to loss of funds. And not the most serious ones, I will emphasize. Just random selection, couple of the vulnerabilities that we found, what solidity patterns or EVM patterns they were based on. And then what I'm going to do at the end of my talk is discuss a bit my experience as an auditor, or of my whole organization, of Dedaub, as a company that does many tens of audits. What do we like to see in Solidity code? So that's the game plan pretty much for today. So let's start with a couple of issues, or not issues, a couple of Solidity patterns that have resulted in vulnerabilities that we have seen. And the first one is kind of the most obvious. In fact, it's kind of a surprise that this has been behind an actual vulnerability, because you all know about it and you know it so well that you would never have any logical error in your code based on that, I'm very sure. and that's the use of this in Solidity. So in most object-oriented languages, well, when you say this.fun and fun, they are the same thing. That's what we are taught in our second year when we first see C++ or Java or anything. So that's kind of a given, right? Well, as you all know, that's not a given in Solidity. These are two extremely different things. One is an external call. It starts a new transaction. The other is not an external call. And how can this result in a vulnerability? In the particular setting where we saw it, obviously, it resulted in a vulnerability because message sender changed. So we could actually use it to bypass some checks. So that's one pattern that's kind of completely innocuous. Everyone knows about it. Not everyone knows about it. You know, obviously, there are people who did not know about it and deployed some code based on that. So what's another one? So this is actually our most recent big vulnerability disclosure. This was a bug that could have resulted in well over $1 billion in damage if we had, if this was actually exploited. So I will challenge you, if you have not seen any of our articles, that's going to be more interesting. If you have, then you already know kind of the answer. I would challenge you to see what might be wrong in a pattern like this, and I will go over it. I'll try to explain it. So there's this contract, and it has two ways to deposit funds. And the first one just says, well, sorry for pointing on the screen that most people cannot see, so I'll point on my screen. I have an underlying token, and I do a completely safe transfer from. So we all know this is a very safe transfer from pattern because we're transferring from message sender to this. That's what we've been taught is the right way to do transfer from, right? So that's the way to deposit to this contract. And there's a second way that says deposit with permit, and this allows transferring from anyone that's given approvals. And before that, it has a permit call. And if you haven't seen it, an ERC20 permit call is an alternative to approve. It's a way to use ECDCSA signatures to actually offline sign a transaction, an approval, and get the approval implemented by calling permit and supplying that signed message. And this looks fine, right? I call permit on the underlying token, and only then I transfer someone else's amount. And that someone else, you know, the ... here, the ellipsis, it includes the target, it includes who signed, so it should be fine. So if you don't know the answer here, I would like you for a second to think, what is the definition of permit in WETH9, in the wrapped ether contract? So in wrapped ETH, the most used ERC20 token, how is permit defined? Visualize it. 5, 4, 3, 2, 1. If you don't know the answer, I bet that's not what you were thinking about. There's no permit, but there's a fallback function. So if I call permit, it doesn't revert. So this is what we call a phantom function. A phantom function is one that the contract code does not explicitly define, but it accepts calls to it without reverting. So we say that WETH has a phantom permit. So going back to why this led to a very significant vulnerability, a hugely significant vulnerability, might have been the largest hack ever if we hadn't disclosed it. Let's look at this. Everyone is using the normal deposit path, the top path. So this contract has like 10,000 accounts that have approved it because they use the regular deposit. And then this down here, this permit is a no-op. WETH accepts it and doesn't revert. So we get to transfer from, and we can transfer anyone's money who has ever given approval because they wanted to use the top deposit function. So that's the source of a pretty large vulnerability. That's kind of one Solidity, EVM, something to keep in mind, kind of something to keep in mind when we're coding. The use of a fallback function, and clearly recent versions of Solidity distinguish at least fallback from receive, So if all you want is to receive ETH, then you don't need to use a fallback. But it is a standard caveat that people should have in mind. So now that we covered a couple of those patterns, a couple of those Solidity patterns, what I'd like to do in the remaining few minutes is give an idea of, however long I can cover, of what we like to see as auditors in Solidity code. And I could title this writing correct code or secure code, but, well auditable code, let's just say. Maybe I'm kind of claiming that it's the same thing as correct or secure, but maybe it's not the right thing, the same thing. So a couple of warnings that we give to everyone whose code we're auditing is, first of all, no auditor will ever have 100% confidence in the code they're reading. There's a spectrum of confidence in any audit. And an audit actually stops when the auditor runs out of time, not when confidence is 100%, because it's never going to be 100%. So what does that mean? If you have well auditable code, that's going to get very close to 100%. Otherwise, the audit will just stop, but the confidence may be at 80%. You don't want that. Okay, so what are good practices for well auditable code? Well, the standard things that everyone, I think, will tell you, and that most good projects respect, is you need to have documentation, comments, good variable names, well-tested code, and a great communication channel with auditors. I think we're not going to go into that. Everyone will tell you this. Excellent practices. We tell people that. Here's what I am going to insist on. The thing that I absolutely love when I'm auditing code is invariance. Some properties that will give me design insights. And those could take many, many forms. So invariants are properties that hold no matter what. And they could be temporal properties or state properties, like this function is only called under these preconditions. Whatever, preconditions on the caller, preconditions on what has happened before, and general invariants such as no ETH balance or no ERC balance, ERC20 token balance is supposed to remain in this contract. You know it when you write code. We need to know that you make that assumption. And because we need to check that that assumption is never violated. So it's great. Part of auditing is just reverse engineering these exact invariants. And I'll show you some examples of things that we have reverse engineered or seen in comments. Of course, invariants don't have to be temporal. They could also be functional. And these are the simplest ones. So these maybe you already do. So you write a field and you say it's denominated in, if it takes an array of 10 tokens, it's denominated in the last of the tokens, or it's in 5 decimal scale. So, or this variable, if it's positive, it means the amount in, if it's negative, it means the amount out. That kind of thing, if you don't know it, you really cannot understand the code. It will take you an hour to reverse engineer it to understand the code. The programmer knew that. Write it. This is extremely useful. And invariants, very much, these are probably the most important kinds for large protocols. They need to be structural. So if you have, say, strategies and you have some policy on what the strategy should do, please write it clearly. So for instance, strategies have to override these functions. Or if a strategy does that, then it should override the reward token function and the reward rate function. So to make it maybe a little bit more concrete, here are actual examples of, half of them are from comments that we actually saw, and I was like, I love you, man. I love you for this comment right here. And the other half are things that I might have taken half a day to reverse engineer from the code. So it's a mix of good invariants in code. Like, you have a function like this, sub until 0, and you get a comment that says, oh, it returns a pair, and the first part of the pair is how much is left of x if we subtract y. The second is how much are we missing from x to reach y, and one of the two is always 0. Love that. That's great. That's fantastic. Now I can go on and understand how it's used. Or something like this. What is this variable or this field of a struct? It's a delta of how much the liquidity is added when this happens. That's great. That's fantastic comments because they give me an interpretation of something that otherwise I would need to reverse engineer with a lot of pain and suffering. And I have, more examples of the same kind, but this is not so you can actually parse them. Obviously, I don't expect you to internalize the spec of any of those in real time. Just by way of example, if you have variables like liquidity outside, what does outside mean? Like, this was something we had to reverse engineer with the developers at some point, and they actually had to write code in a math plotting software to actually explain some of these concepts when they could have, and it was great when they actually did, but it took us 2 days of communication to get to that point. It would have been wonderful if they had documented with an invariant the original intent, the original meaning of, say, the word outside. So that's kind of a sampling of what I encourage Solidity developers to do to develop well auditable code, which I think ends up being more secure code. And here's the unpleasant truth number 2 of auditing. Auditors are not the owners of your project. You are, which means you are, in the end, responsible for everything that goes in there. The auditor comes and says, hey, look, I found a violation here. Well, your job is not to say, oh, what's the least I can do to just assume it away or just fix the minimum? Your way of reacting should be, oh, wow, hadn't thought of that. What else like that might I have not thought about? Because this is obviously coming from a different angle. Can I see my code now from that angle? And I think that with good collaboration of this nature between developers and auditors, we get very, very secure software. So I think that's roughly all I had to say. I'm here, obviously, all day, all week, if people want to catch me for questions. Also, here we have time for questions, I think. Again, I'm Yannis from Dedaub, and if you have a chance, please visit the contract library. Thank you. I could make them available wherever the organizers tell me to upload them. Yeah, obviously they will be public.
Hello. I think your decompiler is amazing, and especially with how you do storage slot inferring. Is your methodology public on that? I think it's only something that you guys do.
I don't think we do anything very fancy for storage slots. So our base decompiler, anything up to the 3 address code that we use for all the vulnerability analysis, that's open source. That's an open source repo. And Neville can give you information, but he has it on GitHub, and so that's open. What we do for storage slots is just we see the constants that go into sstores and sloads in the code, and that's how we reverse engineer storage slots. And that's why sometimes we'll miss some of them. So in the next version, what we will actually do is we will also give you a way to dump the entire storage of a contract, which you can already do with command line tools, so it's not a big thing. That's why we haven't needed it so far. But for inference of storage slots, we don't do anything funky. Now, if you mean data structures, mappings and arrays, there we do have logic. So there we do something a little funkier.
Right.
Yeah.
Right. I've noticed from using your tool that oftentimes you can determine where like an owner variable is stored. I'm assuming based off of knowing that it's an address and knowing that's in a require statement.
It's actually simpler than that.
Okay.
The names of fields just come from the shortest public function that accesses the field. So it's called owner just because the shortest thing that returns that field is called owner in the public signature. So that's the heuristic there. There's someone over there.
Well, if nobody wants to have a go, I'll have a go. So there's a lot of airplane accidents that happen because what happens with the pilots is that they have a sort of a wrong view of the world. They sort of build an incorrect view of the world, And eventually, they basically cannot get out of it until they crash into the ground. So this is a relatively typical way of crashing an airplane. It's called controlled flight into terrain. So you have full control, but you crash nevertheless. And when you were talking about these comments, and they explain to the auditor what's happening. What I'm thinking is that maybe what's happening is these people who write the comments, they're sort of the pilots of this airplane, and they're writing these comments, explaining their view of the world, of how they think this system is supposed to work. And now you're the auditor, and instead of having an independent view of like, okay, well, I'm going to build my own view of the world, and I'm not going to crash into this ground, right? I'm going to build my own view of the world and understand how this system works, and then maybe, I find the issue that these people didn't see. But if you actually look at the comments, you might, build the same, state of the world as the people who are, driving this plane or whatever you want to call it, and, crash into the same place that they're crashing into. So I'm guessing, are you, like, there's a clear, I think you understand the question, so
yes,
I'm just going to let you answer.
Yeah, so this is a big kind of philosophical debate in the auditing community. There are people who will tell you, I don't read comments, I don't communicate with developers at all, I want to build my own view of the code. That's not what we do. We trust our own sense of thinking in devious ways. So we typically do 2 passes over the code, and the second time we try to think like people who are thinking about this in very sneaky ways, trying to violate every assumption. So we trust ourselves on that. And obviously, if someone doesn't want any communication from a developer, if they want to build their own view of the code, they can actually absolutely do that, just ignore the comments. It's not my philosophy. I want to first see what's the correct view before I try to break it. I need to understand what the developer has in mind as their invariants before I try to break them. And it's my job to break them, so leave that to me. Just give me your view, and it's my job to see things from a different angle. Also, I think it's not exactly practical to reverse engineer everything. You know how much time it would take to reverse engineer everything? It would be like, it would make every audit like 3 times as long, and people are paying for audits quite a lot these days.
Okay, I see there are more questions, but again, we are running quite late in time, which means please find Yannis after his talk. You will stick around, I guess, and ask him any question you have in the lunch break or in the upcoming coffee break, which we will have after this talk. So yeah, a round of applause for Yannis. Thank you so much. That was great.